Okay, so this video is going to be an introduction to light and electromagnetic waves, which are light. Okay, so let's go ahead and get started. The first thing I want to talk to you about, though, is how light is created, where it comes from. Okay, and so light is a form of energy that's released by an accelerating electron, and there's a couple ways that could happen. So the two ways we might think about this, first of all, if this was an atom, okay, and it has its electron orbitals, this would be the nucleus, okay, and these are the orbitals right here, okay, nucleus made of protons and neutrons. Then in the orbitals around it we have electrons, okay, and these electrons will spontaneously kind of, depending on where they're distributed, they'll kind of spontaneously jump down. When they do, they release some light, okay. And sometimes light will hit them, causing an electron to jump up. Okay, so it's the light basically hits the electron, gives it energy, causes it to jump up to a higher frequency or a higher orbital shell, and then at some point it'll drop back down, emitting that light. Okay, there's other things that can cause an electron to jump up, though, and it could happen when there's molecules bumping around, hitting each other, stuff like that. But anyway, light is created when these electrons jump back down. Okay, and this is what's going on in the light in your house, the light in the classroom. Okay, whenever you see a light bulb, you have molecules where these electrons are jumping back down and sending out that light. Okay, and this is the same thing going on in the sun. There is another way that we can create light, though, and this is actually happening with your phone, your cell phone right now, whether you realize it or not, and that's through an antenna. Okay, what an antenna does is it causes electrons to accelerate. It sends them this way and makes them turn around, come back this way, and these accelerating electrons are what cause the creation of light waves. So really, the creation of light comes down to the acceleration of electrons, okay? And these are kind of the two ways that we see it happen, all right? And what happens is it creates this kind of wave called an electromagnetic wave. Okay, and we call one little like emission from an electron, we call that a photon, okay? And a photon is kind of that bundle of energy released by the electron. And light then would be a stream of these photons. Okay, so at any moment there's a stream of these photons coming out of the lights in your house, coming out of the sun, coming out of your phone. They're everywhere. Okay, and they're all over the place. Now the thing about light is that it travels at this speed, about 300 million meters per second, or 3 times 10 to the 8th meters per second. Okay. And this number, and this is the speed of the light in a vacuum. So light actually travels different speeds depending what it's traveling through. But this is how fast it travels in a vacuum. This is when light would be traveling its fastest. And this number is a constant, meaning this is the only speed that light travels in a vacuum. It doesn't travel faster, it doesn't travel slower. This is how fast it travels. Now we'll get into later some of the complexities that come out of that, because this is the only thing in the entire universe with a fixed speed, and for the speed to be fixed is significant in that it means it's fixed for everybody observing the same thing no matter how fast they are moving. Now that's a little bit abstract. We'll get into it later. You don't need to understand that now. Okay, but some other interesting things. So 300 million meters per second is the same thing as 186,000 miles per second. Okay, and the sunlight takes over 8 minutes to come from the sun to the earth. Okay, so just kind of think about this in your head. If the sun were to explode one day, it would take us 18 minutes and 17 seconds before we found out about it, because that is the rate at which the information and the light from the sun takes to reach us. Okay, and so the light that reaches us on the surface of the earth from the sun is already 8 minutes old. And actually, it takes millions and millions of years for that light to actually leave the sun from the center, and then once it does, it goes on that journey, 8 minutes to reach us, but really it goes on forever. And so we see these stars in the sky, and they are hundreds of millions of light years away. A light year is a distance measured by basically how far light would travel in a year. And so you get these stars that are hundreds of millions of light years away, and so the light that we see from them is hundreds of millions of years old. And so when somebody is studying astronomy, they're looking into the past. They're studying the history of the universe because they're seeing light from things that happened a long, long time ago. Okay, so electromagnetic waves, which is what light waves are, they are produced by the accelerating electrons, and whereas mechanical waves, which we've been learning about, have to travel through something or need some kind of material in order to propagate. Electromagnetic waves just need themselves, and that's why they're able to travel through space. Because like the sun is super, super loud, but we can't hear it because there's no air for the sound from the sun to travel through. Okay? But these electromagnetic waves get to us because they don't need air. They can travel through a vacuum. Okay? And so it's a transverse wave because the energy is perpendicular to the direction of these oscillations. Okay? And so this right here is kind of beyond what we've covered so far. It requires some knowledge that we haven't discussed yet, but it's basically composed of electric and magnetic fields, which are very closely related to each other, and that's why it doesn't need a medium to travel through. These basically cause each other, and so they kind of switch back and forth between them. Okay, and these electromagnetic fields occur at right angles to each other. And so there are lots and lots of kinds of light, lots and lots of kinds of electromagnetic waves that all travel at the same speed in a vacuum, 3 times 10 to the 8th. Okay? And here's kind of all our different classifications of light waves. There's kind of a continuum, and this is what you're going to be investigating later this week, this electromagnetic spectrum, all these kinds of light. But these are all different kinds of the same thing. All of these are light. They all travel that same speed, but they have different amounts of energy, all the way down from radio waves to microwaves, infrared, visible light, UV light, X-rays, and gamma rays. You've heard of all of these things, but you've heard of all of them separately. Probably you didn't realize that these are all the same. The way that your car receives signals to turn on the radio is the same way that your microwave heats food. It's the same reason why you're able to see. Okay, it's the same way that we're able to see through people's skin to their bones. All right, all of these represent the same thing, but down here is where we have the lowest energy, and up here is where we have the highest energy. Now microwaves, this is kind of what you're going to see. This is what gets emitted by your phone, and this is how your phone communicates with so like in the classroom, we have a Wi-Fi router attached to the ceiling. You'll see it with the blue light, and it's sending out microwave radiation, communicating with your phone to connect to the Wi-Fi, communicating to the Chromebooks. Okay. And here's a quick overview of the electromagnetic spectrum, and this is organized based on the size of the wavelength. Okay, so radio waves have a wavelength of 10 to the 3rd meters, or about 1,000 meters. Okay, all the way down to gamma radiation, which has a wavelength of 10 to the negative 12th. Okay, which is less than a trillionth of a meter. Okay, so these are a very, very wide range of wavelengths and frequencies, and so this kind of represents all the different kinds of light, and anything smaller than this would be considered a gamma ray. Anything bigger than this would still be considered a radio wave. Okay, And now let's just make a quick comment on how big this is. Okay, this is some radio waves are bigger than others because this kind of spans the range from 10 to the third all the way to 10 to the negative second. Okay, and so think about your car. You have FM radio and you have AM radio, and you can even see the frequency of those radio waves as you turn the dial. And what it turns out is that the AM radio waves are lower frequency and higher wavelength, and they're so big that you might notice that when you drive under it through a tunnel, you kind of lose the radio, and it's because their wavelength is so big that it can't fit under the tunnel. All right, and the other thing I want to mention is that anything with a wavelength, any physical object that is smaller than the wavelength of visible light are things that we can't see because they are too small for light to reflect off of. Okay, I mean, we can't see this stuff either, but we can look at these things with a microscope. These things over here are too small for us to see with a microscope because there's no light to reflect off of them. And so then we use tools like electron microscopes because they go to greater levels of precision. Okay? Okay, so here's a quick question. When light travels through space, the short wavelengths go what compared to the long wavelengths? You should have chosen the same speed as, because all light travels the same speed through the same medium. Which of these types of light has the highest frequency? The answer is ultraviolet. It has the lowest wavelength, highest frequency, and highest energy of these 4 types of light. To wrap this up, I'm going to really quickly talk about one of the activities you're going to be working on this week, in which we're going to take a 1-meter strip of paper. You'll be working with a partner. You're going to take a 1-meter strip of paper and break it up into segments, each representing a power of 10. So 10 to the 0, 10 to the first, 10 to the second. So this is a logarithmic scale because it goes by powers of 10. And so on, all the way, I believe, to 40. Okay? And these units might be slightly different. I'll have to double check with the thing. It's on the instructions, so make sure you read the instructions carefully. I think these are actually going negative instead of counting it. I can't remember if I have it listed by frequency or wavelength. We'll see. So anyway, the reason I want to mention this though is you're going to be kind of going through and showing like how wide the different bands of the spectrum are for the different kinds of light. And somewhere in the middle we'll have a really small narrow window that represents the light that we can see. And then to the left and the right are all these different kinds of light that we can't see with our eyes. But just because we can't see them doesn't mean they exist, okay? Or that they don't exist. Sorry. But one of the things I want to point out is this. So let's say that you're in that segment trying to do light, and this says something like 10 to the 7th. I don't remember, so I'm just making up some numbers. 10 to the 8th, and so on. And let's say that you want your region to start at like, instead of at a power of 10, you want it to start like 4.2 times 10 to the 7th. Well, this is pretty simple to do. 10 to the 7th, 10 to the 8th, we can break this up into like 10 little segments. Okay, so 4.2 would be like around right here. And let's say it stops at like 8 point something times 10 to the 7th. Well, that's 4, 5, 6, 7, 8. So that might go to like right here. So this would be that window if you had to start and stop in those little segments between 10 to the 7th and 10 to the 8th. Okay?